In this video, we're going to be looking more in depth at infinite limits and limits at infinity. We've talked about these before from an intuitive standpoint, and we're going to continue with the intuitive view of a limit here. Later, at the end of this chapter, we will discuss the formal definition of a limit, and we'll get a little bit more precise about what exactly the limit is mathematically. For now, though, we'll stay with the intuitive version. This section is actually out of section 4.6. The textbook covers the limits at infinity and infinite limits later than I'd like, so I always move this section of 4.6 forward. There's another part of 4.6 that we'll cover later on. Let's talk first about what exactly an infinite limit and a limit at infinity is. An infinite limit is when the y value is going up forever without bound. So for example, right here, you can see the y is going up forever. That's what we mean by an infinite limit. The y value is approaching infinity. Now, what do we mean by a limit at infinity? A limit at infinity, that word at means it's the x value that's approaching infinity. So as x moves to the far right, what does it look like the graph is doing? Now, if you look at this example here, you can see that as you go to the right, the y value goes to infinity. So we have an infinite limit at infinity. However, there are graphs that don't exhibit this behavior. We could have a graph that does something like this, where it approaches, say, one particular y value as x goes to infinity. In this particular case, we would say that as x goes to infinity, moves to the far right, the end of the graph, it looks like the y value approaches 1. This is not an infinite limit because the y value approaches a finite real number, but it is a limit at infinity. Let's take a look now at the learning objectives, and I'll share my screen with you so we can get more in depth. Here are the learning objectives for this part of 4.6. We're going to calculate the limit of a function as x increases or decreases without bound. That means the far right of the graph and the far left of the graph. So way off to the sides are what we call end behavior of the graph. Then we're going to learn to recognize a horizontal asymptote on the graph of the function. I drew one of these previously when I gave the example that you see here on the left. As the function moves to the far right, the end behavior as x goes to infinity, the y value approaches a horizontal asymptote of the constant function y equal 1. Finally, we're going to use our knowledge of what we have learned in the first two parts to estimate what we believe the end behavior of a function will be. And of course, end behavior means as x increases without bound or decreases without bound. We're going to start with limits at infinity. That tiny word at means it's the x value that's going to infinity or to negative infinity. To fully describe the function, we need to know what the behavior at the ends of the graph looks like. So first, we're going to start here with the horizontal asymptote, like the one I drew previously. Recall that the limit of a function as x approaches a equal to L means that the function values, the y values, get arbitrarily close, infinitesimally close to L as long as x gets very close to A. Not at A. We never actually reach A. We just get close to A. We can extend this idea to limits at infinity. So instead of having a finite real number for A, we're going to replace that with either infinity or negative infinity. In the graph that you see here of the function 2 plus 1 divided by x, we can see that the function as x goes to positive infinity is approaching the constant function y equals 2. We would say then that the limit as x goes to infinity of f of x equals 2. This is how we would write it right here on the left. Notice on this one that as we go to negative infinity, as the values of x decrease without bound, going to the far left of the graph, it also approaches the same horizontal asymptote. This does not always happen. Don't assume because you have one horizontal asymptote on the right that you'll have the same one on the left. That does not always occur. In this case, though, it did occur. So we would then represent this limit as x goes to negative infinity as also being 2. When we look at the table values that you see here in the center, you can see that as we increase the value of x to larger and larger values, and it looks like it's cutting off part of mine, the value gets closer and closer to 2. Over here, as we go to negative infinity, as the values get smaller and smaller for x, the y values again get closer and closer to 2. Let's talk about the informal definition for a limit at infinity. We say that if the function becomes arbitrarily close to L as x becomes sufficiently large, yes, what does sufficiently mean? We'll have to make that more precise later. Then we say the function has a limit at infinity, and we write it like this. We have a similar definition as x goes to negative infinity. We say the function becomes arbitrarily close to L for x less than 0 as the magnitude of x becomes sufficiently large. Then we say the function at f has a limit at negative infinity, and we write it using this limit notation here. Notice that when we saw the absolute value of x, I read it as the magnitude. That's the best way to think of absolute value, the magnitude of what's inside. Now let's take a look at the informal definition for the horizontal asymptote. If we're looking at the horizontal asymptote and the limit of the function as x goes to positive infinity is L, or the limit of the function as x goes to negative infinity is L, then the line L is a horizontal asymptote of the function f. Again, it does not have to be the same L on the left and on the right. We'll see that this only happens that they're the same when we have a rational function, the ratio of two polynomials. When it's not a rational function, we can get different horizontal asymptotes at the end behavior. Now, a function cannot cross a vertical asymptote because the graph must approach infinity or negative infinity. The vertical asymptote is coming from a 0 in the denominator that did not cancel. We cannot divide by 0, so it is impossible to cross over or touch or intersect a vertical asymptote. This is not the case with the horizontal asymptote. It is possible with the horizontal asymptote to cross over it. In fact, you can cross over it infinitely many times. You'll see in this graph here of cosine x divided by x plus 1 that the graph does approach the y value of 1 as x goes to positive infinity. But in fact, it is going and oscillating above and below that line infinitely often. Notice, however, that the limit exists because the oscillation is getting tighter and tighter around that constant line. We say that this is damped oscillation, meaning that it's decreasing in amplitude as it moves to the right. In some ways, I think of this as like a vine choking a tree and getting tighter and tighter around the tree. Let's now turn our attention to example 1 and see if we can apply what we've learned. We want to evaluate the limit of the function 3 plus 4 divided by x as x goes to infinity and negative infinity. So we want both end behaviors. We want to see what the horizontal asymptotes might be if there are any. Now, how are we going to do this? Well, the simplest way to do it is to use your knowledge of what happens as x goes to infinity. When we're looking here as x is going to infinity, we can see that if we evaluate it, got to find my pen. Let's take the limit to the right first. As this is going to infinity, remember that the first thing we always try to do is substitute the value of a in for the variable x. In this case, it's not actually a value, it's a direction. However, if I envision what happens as x goes to infinity to the fraction 4 over x, I can visualize that this becomes 4 divided by ever increasingly large numbers. The larger the number, the smaller the fraction 4 divided by that number is. In fact, 4 divided by something approaching infinity is approaching the value of 0. This means that a constant divided by something approaching infinity goes to 0, as we saw in the previous section. And this gives me 3 plus 0, which is 3. If I take the limit as x approaches negative infinity, then I'm also going to get the same value. Now, before you think, oh, they're exactly the same, there is a slight difference. So let's take a look at what this slight difference might be and think about why it's happening based on our graph. Both the left and the right approach the horizontal asymptote of 3, but in the first limit, as x approached positive infinity, the numbers became larger and larger and larger, but were positive. So 4 divided by a positive will be a positive number, which means that this is actually a little bit more than 3. It's approaching exactly 3, but from numbers above 3. So the graph must be coming down towards the constant line y equals 3. When we look, oops, I lost my negative. When we look at the second limit as x approaches negative infinity, notice that again, as x goes to negative infinity, the numbers here are increasingly large in magnitude, but all negative. So 4 divided by a negative will be a negative, which means that these numbers will be slightly less than 3. Still approaches exactly 3, but from numbers below 3. Let's click on the graph so that we can verify that this is what happens. Give it a minute, and we can see it right here. Now, if I look at this particular one, and I want to put on here the graph of 3, I can put in y equals 3, and then I would like to make it a different color so it doesn't blend in, and make it dashed. You can see in the graph now that on the left, as x approaches negative infinity, it does approach 3 and will get ever closer, but from numbers below 3. And on the right, it again approaches y equals 3, but from numbers above 3 and getting ever closer. Let's now talk about limits at infinity, infinite limits at infinity. When we talk about infinite limits, the first part means y is going to infinity or negative infinity. At infinity means x is going to infinity or negative infinity. Combining the two, it means the end behavior of the graph has to be going up forever, down forever, or one up, one down forever. So an infinite limit at infinity is somewhat similar to the graph of x squared or x cubed. In both cases, the end behavior approaches infinity or negative infinity. In this case, we'll write that the limit as x goes to infinity or negative infinity equals infinity or negative infinity, but that does still technically mean the limit does not exist. The y value, the value of L, must be a finite real number for the limit to truly exist. We write infinity or negative infinity because it gives us more information about the graph, but it doesn't mean the limit exists. Infinity and negative infinity are not numbers. Now, we want to take a look at another figure, and we want to look at the values in a table and see what's happening to the graph. This is the graph of x cubed. As we look at the graph of x cubed, scrolling so you can see it all, as we move to the right, you can see that as x approaches positive infinity, the y value also approaches positive infinity. Looking at the values down here, as the x value gets larger in magnitude, the y values get massively larger in magnitude very quickly. When we're looking at the second table, we can see that as the numbers go to negative infinity, become smaller but greater in magnitude, the value for the function also decreases without bound. The magnitude gets larger, but they're negative, so they get smaller. In this case, we can see that the limit as x goes to negative infinity of x cubed must be negative infinity. So we would write the limit as x approaches positive infinity of x cubed equals positive infinity, and the limit as x approaches negative infinity of x cubed equals negative infinity. Technically, neither limit exists, but we write those values to give information about the graph. Our informal definitions for infinite limits at infinity are very similar to the ones we saw before. If the function has an infinite limit at infinity, we write it using that notation if the value of y becomes arbitrarily large for x sufficiently large. What does arbitrarily large mean? We'll make it more precise in section 2.5, but for now, think of it as having no ceiling value. There's no upper bound. It just keeps getting bigger and bigger and bigger, no matter what happens. We say the function has a negative infinite limit at infinity, and we use the notation right here, provided that as x becomes sufficiently large, the function value is negative, but the magnitude becomes also sufficiently large. Now, let's take a look at what's called end behavior of a function. The end behavior is what we're talking about at the far right and far left of the graph, the ends of the graph. Now, the behavior has several different options. The function could approach a horizontal asymptote, y equals L. The function could approach infinity or negative infinity, and it could do neither one of those. It could not approach a finite number or negative infinity or infinity. It may have some oscillatory behavior. For example, if we think of the graph of sine of x continues to oscillate between 1 and -1 forever as x moves to the far right and the far left. It never gets close to one finite real number. It goes between a range of numbers from -1 to 1. And we would say then that the limit of sine of x as x goes to infinity does not exist. Due to oscillation. Let's talk about the end behavior for polynomial power functions. Now, when we talk about a polynomial, what exactly do we mean? Well, there are a couple of conditions to be a polynomial. Polynomial is one or more terms with real coefficients multiplying by a constant. The constant has to be real, but that means it could be pi or the square root of 11. And the variable in the numerator must have a whole number exponent. And whole numbers are numbers like 0, 1, 2, 3, and so on. Now, a power function consists of a single term polynomial where there's no coefficient. So it's pretty much a basic building block, x to the nth power. The limit of x to the nth power as x goes to infinity is going to depend on whether n is an even number or an odd number. You know that the graphs of x squared does this, and the graph of x to the fourth gets a little flatter in the middle, but it still goes up. Next to 6 gets flatter still, but it still goes up. When you're looking at those, that means that the behavior of these is going to go to infinity, right? If you're looking at one that is odd, if you're looking at the limit as x goes to negative infinity, well, then that depends. So on the right, the even ones go up always. And on the left, they go up always. On the odd powers, on the right, they still go up. But on the left, they go down. And that's because if you take a negative value to an odd power, it stays negative. So if they're negative and you're going to the left as x goes to negative infinity, it approaches negative infinity. And again, you could have a cubic or a fifth power. They get a little flatter, but they're still basically the same. Let's take a look at these two pictures here and talk about what's happening in the graphs. You can see that there's one in the center, which is a dark blue in color, and it's coming down. It gets much flatter than an ordinary parabola down here. So I know it must have power greater than 2. And in fact, that one has power of 6. But because it's even, both the right in behavior and the left in behavior approach positive infinity. The graph of x squared is the one that is the widest opening in this teal color here. And then x to the fourth fits in between those two graphs. X to the fourth does get flatter than x squared, but not as flat between -1 and 1 as x to the 6th. In all cases, because the power is even, the right in behavior and left in behavior is positive infinity. Now let's look at the next graph, which is the graph of odd power functions. In this case, all of our power functions basically have this behavior, and you'll notice they even included the identity function y = x. Now, our picture is not to scale, which is why y = x does not look like it's at a 45-degree angle. The distance from 0 to 5 on y is less than the distance from 0 to 5 on x. When we look at these graphs, you'll see that the basic cubic is in orange, which is fitting in between some of these graphs. And you'll see that it comes up, flattens out between -1 and 1, hits horizontal at one moment at 0, and then increases again, and then rapidly outside of 1. On the right side, it goes to positive infinity. On the left side, it goes to negative infinity. The fifth power, it's hard to tell in here, but it gets flatter between -1 and 1 than x cubed, but it's steeper between -1 down to -infinity, and between 1 and infinity. So you can see in the case where the power is odd, we have different end behavior on the left than we have on the right. Let's now predict what the end behavior would be for this one. You'll notice that this is not technically a power function because it has a -3 multiplied by it. Is that going to affect it? Well, the answer is yes, of course. What does it do to the graph? The negative is going to reflect it across the x-axis, and the 3 is going to stretch the y values, make them faster, 3 times faster. So if it was at 1, it'll now be at 3, right, for the same x value. What would a normal x to the 4th look like? A normal x to the 4th would look something like coming down, flattening out, and then going back up again. Multiplying by -3 is going to make the graph open down. It's still going to flatten, but it's going to be steeper, and it's going to happen faster. In this case, the -3 reflects the end behavior. So if we're looking at the limit of the function as x goes to infinity, we get -infinity. We get the same as it goes to -infinity. So the limit as x goes to positive or -infinity is going to be -infinity, right? Far right, far left goes down forever. Now we want to talk about end behavior for polynomial functions. When we're looking at polynomial functions, remember we have real coefficients, whole number powers on the variable when written in the numerator. So 0, 1, 2, 3, and so on. The a0, of course, this term, can be written as a0, which is a constant like 5 or pi, x to the 0. Remember that x to the 0 equals the number 1. Any number to the 0th power except 0 is 1. So we can represent this using our rules for polynomials. What happens when you go to the far right of the graph and the far left, when the numbers become massively large in magnitude, is that only the highest degree term is going to affect the end behavior. Now, the others do have an effect on the graph, but it becomes less and less as the graph moves further and further to the ends of the graph. Now, you want to be careful and make sure that you actually have the highest degree term. Textbooks are known for writing things like this: 3x cubed minus 5x to the 4th plus 2x squared minus 7. And they want you to think that the highest degree term is the 3 because it's written first. It's not. The highest degree term is going to be the one that you see right here in the middle, that -5x to the 4th. As x approaches infinity and as x approaches -infinity, this polynomial is going to approach the graph of just the highest degree term, -5x to the 4th, like an asymptote. Now, the lower degree terms do have an effect, but they are not what determine the end behavior. That's determined by the highest degree term. Now, let's see why this is true. Oops, it's not wanting to scroll for some reason. There we go. If we take the polynomial and we factor out of every term a sub n x to the n, then we're dividing each term in the original polynomial by the leading coefficient. When we do that, we get a ratio of constants. But notice that because this is the highest degree term, all of the ones except the first one end up with an x to a power in the denominator. Now, what happens as you go to infinity or negative infinity? As you go to infinity or negative infinity, this constant over x or constant over x to a power approaches 0. So all of these terms zero out, and it approaches the graph of just the leading term with the a sub n attached. As we saw previously, multiplying by a negative will reflect the graph. If it was like this, it'll be like this. So it does affect the end behavior. Now, this is not true near the origin. When you're near the origin, these lower degree terms have an effect. Let's consider the polynomial 2x squared plus x minus 6, the one that you see here. Near the origin, let's say at x equal 1, which of the terms, 2x squared plus x or negative 6, has the most effect on the graph or the y value? When you're thinking about it, if you plug in 1 to each term that has a variable, the first term becomes 2, the second term becomes 1, but the last term, the constant, is a negative 6. The negative 6 has the greatest effect on the y value. However, as we go to positive infinity or negative infinity, what happens to the effect of each term? Let's say we go to a medium-sized number like 1,000, which really isn't very big in the grand scheme of things. If we think about plugging in the value of x equal 1,000 into the first term, we get 2 million. The middle term becomes 1,000, and the constant term stays negative 6. Now, who's got the power? As you can see, as the numbers get massively large, the highest degree term begins to dominate the shape of the graph and pulls it like an asymptote towards the graph of the function consisting of just the highest degree term. Here's the graph of 2x squared and the graph of 2x squared plus x minus 6. You can see in the center of the graph near the origin, they're not that close together. They're not alike. But as you move to the far right and far left, the far right especially, the graph of x squared plus x minus 6 here in blue gets infinitesimally closer to the graph of x squared. Now, it'll never be exactly, or 2x squared. It'll never be exactly on that graph because the plus x and minus 6 terms do have a small effect, but it gets closer and closer to that graph. The same would happen on the left if I had zoomed out far enough. Now let's go to example 3, and let's let you practice this on your own. Pause the video and work out the problem, graph the function, see if it verifies what you thought would happen, and then we'll come back and compare our answers. So let's see what we have. Remember that the end behavior of a graph is dominated by the highest degree term. So the limit of this cubic function as x approaches infinity approaches the limit as x approaches infinity of the highest degree term, which is just negative x cubed. If we substitute positive infinity in place of the x and cube it, we'll still have positive infinity. But the leading constant, the leading coefficient, is a negative 1, which changes it to negative infinity. What happens as we approach negative infinity? Again, the graph of the cubic polynomial will approach like an asymptote at end behavior the graph of the highest degree term, negative x cubed. In this case, we're approaching negative infinity. So when we cube it, we still have negative infinity. Then a double negative pulls it to positive infinity. Let's look at the graph and verify that that is indeed what happened. You can see here the graphs of the two functions. The highest degree term, negative x cubed, is in blue, and the actual function we're trying to find a limit for in green. Maybe I should change the color since blue and green aren't a good combination. Let's change this other one to red. All right. When I'm looking at these, notice that as I observe the graph, they both are going to go towards positive infinity as x goes to negative infinity, and they both go to negative infinity as x goes to positive infinity. And that's the result that we had in our example. Let's now discuss a rational function, the ratio of polynomials. We know that for a polynomial, the end behavior mimics the behavior of the highest degree term. What happens then when we divide a polynomial by a polynomial? That's the ratio, hence rational function. When we're looking at this, as you might expect, the limit of a quotient is the quotient of the limits, provided the denominator is not zero. We know the numerator is a polynomial, so it should be dominated by the highest degree term, a sub n, x to the n. The denominator is also polynomial, so it should be dominated by b sub m, x to the m. That means that this particular rational function on end behavior will approach the graph of the ratio of the highest degree terms, a to the n, x to the n, divided by b to the m, x to the m. That's what's going to happen for a rational function. You can think of this as kind of like a tug of war between the highest degree term in the numerator and the highest degree term in the denominator. What can happen? Well, there are three different cases that we can see. If a sub n x to the n is the highest degree term in the numerator and b sub m x to the m is the highest degree term in the denominator, what becomes the end behavior? If they're both to the same power, they're both x squared, or they're both x cubed, or they're both x to the 42nd, then they will cancel in the ratio of the highest degree terms, and we'll get a constant, meaning that we get a horizontal asymptote, both to the right and to the left. This is the case where we have a function and the end behavior on the left and the right for a horizontal asymptote is the same. It will approach the same horizontal line, and it will be given by the ratio of the leading coefficients, a sub n divided by b sub m. What if the power is in the denominator? Let me write down some examples so that you can see what this is going to look like. Let's suppose I had 5x cubed over 2x cubed, just the highest degree terms. The x cubes will cancel, and this is going to approach the graph of y equals 5 halves. What if instead the degree of the numerator is smaller than the degree of the denominator? Let me give an example of that one. Suppose I have 5x cubed divided by 4x to the 5th. Well, you know from cancellation that all of the x cubes in the numerator will cancel, and this will become 5 divided by 4x squared. Now, as x goes to either positive infinity or negative infinity, that's going to approach 0, which means there is still a horizontal asymptote, and it's given by the x-axis, y equals 0. What if the degree on top is larger than the degree on the bottom? In this case, there is no horizontal asymptote. For this one, let's take 14x to the 7th over 2x to the fifth. This is going to reduce to 7x squared. This means that as the function moves to the far right and far left, it's going to draw in closer to the graph of x squared on the edges. Crazy, I know, but that's what's going to happen. The graph of x squared is not a line, so we don't have a horizontal asymptote. We're going to study this third case more in depth when we do 4.6 part 2. Let's now look at some examples. Oh, by the way, I sometimes call this the Bill Gates or Jeff Bezos rule because they with the most money rule. And in exponents, the highest exponent, he rules in behavior. Let's now look at example 4. Pause the video, estimate what you believe the end behavior, the limit as x approaches infinity, and the limit as x approaches negative infinity is going to be. Graph the function to make sure that your conclusion is correct, then turn the video back on. On this particular problem, the limit as x approaches infinity of the ratio of 3x squared plus 2x minus 1 to a denominator of 5x squared minus 4x plus 7 approaches is not equal to, don't put equals here, put an arrow, approaches the graph of 3x squared over 5x squared, the highest degree term in the numerator and the highest degree term in the denominator. Don't forget to include the leading coefficients. They do have a strong effect on the graph when they're attached to that highest degree term. The x squareds cancel, and I get 3/5. That means on the far right, it approaches the horizontal line, y equal 3/5. Because nothing would change when I approach negative infinity, I also get 3/5 on the left in behavior. Now let's look at the graph. This is kind of an interesting little graph. It's kind of a cool little graph. It's nice and smooth, which we really like in calculus. And notice that I have the dotted line y equal 3/5 in black and the others in purple. It's coming up to the right. It comes above the horizontal asymptote, and then it comes back down to approach it. On the left, it stays below the asymptote and approaches the asymptote from below. So although the end behaviors are both approaching 3/5, they're approaching it in a different manner. We'll look more in depth at how the derivatives and limits affect the shape of the graph when we get into chapter 4. Let's now return to the notes, and I would like you to try example 5 on your own. In this case, whether we're going to infinity or negative infinity, the graph of this function will approach 2x over x squared, the ratio of the highest degree term in the numerator divided by the highest degree term in the denominator. They're not equal because of the +1, +6, and +5, but it approaches, which is why we use an arrow. Now, when we look at this, this reduces and it becomes the limit of 2 over x. In both cases, positive and negative infinity, it becomes 0. However, note that in fact, we can predict a little bit more about the graph because as x approaches positive infinity, all of the denominator values are positive, which means it is getting close to 0, but from numbers above 0. So we say it approaches 0 from above. Now for the next one, as we approach negative infinity, all the denominator values are negative, which means that those values are negative. So it is approaching 0 from below. Now on a test, I would not expect you to give me the above below. You can simply give me 0. Let's look at the graph and see if our suspicions are correct. And you can see in this fascinating graph that it does come above the graph as we move to the right and then comes back lower faster and faster, getting close to the x-axis. On the left side of the graph, as we approach negative infinity, the graph stays below the axis and approaches zero from below. Let's now look at example 6. Pause the video, work it out, and then turn it back on, and we'll compare our answers. In this problem, we have what I call a top-heavy rational function. The degree of the numerator is 3, and the degree of the denominator is 1. That means that when this graph approaches the ratio of the highest degree terms, it's top-heavy. There's more power on top than on bottom, so the top is going to pull it in that direction. When I reduce the x cubed over 3x, I get 1/3 x squared. I know because it's a power function type where the power is even that it goes to positive infinity. When I look at it as x approaches negative infinity, everything is the same to the end. And again, because it is an even power, it also goes to positive infinity. Let's now take a look at the graph of this function to see if our suspicions are correct. You can see here in blue the graph of the function whose end behavior we're trying to find. The ratio of the leading terms gives us x squared divided by 3, which is graphed in green. When you look at these, you can see that they're going to get closer as they go higher up. If you want, you can scroll out so that you can see that they become closer and closer. A more effective way might be just changing the vertical axis and not the x-axis. Let's now turn our attention to example 7, the last one in this section. Let's determine the end behavior for the function x squared plus x minus 2 divided by x squared minus 3x minus 4. Go ahead and do your work now. In this problem, notice that the degree of the numerator is 2 and the degree of the denominator is 2. Both the numerator and denominator are polynomials, so I predict that I will have the same horizontal asymptote on the far right that I have on the far left, because it is a rational function and the degrees are equal. In this case, it's going to be the ratio of the leading degrees, x squared over x squared, which reduces to 1, and the limit of a constant is the constant. This applies to both sides. Now, on an exam, you don't need to write out all of this. You know it's a rational function. You would probably be able to look at this and go immediately to the solution. But it's always a good idea to write down some work in case you make a mistake on the constant. Let's look at the graph and see what it looks like. When we look at the graph, we see the graph of our true function in red, and we see the horizontal asymptote here in blue. Now, I did not put in scratch that. You can see as x goes to positive infinity that the graph is approaching y equal 1, coming down from above. As the graph moves to the far left and x approaches negative infinity, it also approaches y equal 1, but from below. We'll get more into that behavior, that above below, when we take a longer look at section 4.6 and chapter 4 in general. Let's now take a look at the behavior of functions that are not ratios of polynomials. What if we have a radical involved? What's that going to do? Now, unfortunately, the textbook doesn't cover these, but I always put these on exams, which is a major hint for those of you in my class. We're going to start by clearing up what the square root of x squared actually is. Do not tell me ever that the square root of x squared is x. It is not. It never was. I know from high school that students come out believing that the square root of x squared is x. But that's because in the directions to the problems, which you never read, it said, assume all values are positive. If you assume all the x values are positive, then it is true that the square root of x squared will be x. However, in college, we make no such assumptions. X could be negative or positive or 0. In this case, what happens is if the value is already positive before you start, then the square root of x squared is just the value x. If, however, the value of x was negative to start, then when you evaluate the square root of x squared, you're taking the absolute value of that number, which makes it be positive. But if the number was originally negative, you have to write that as negative x. The x is negative, so a negative negative gives you a positive. This is going to affect the graphs quite a bit. In these particular values, these particular functions, we're going to see that the horizontal asymptote on the left and the right may not match. In fact, probably will not match. The square root of x squared is the absolute value of x. It is a piecewise defined function. If x is not negative, it's just x. If x is negative, you replace it with negative x. Now, it's still going to be the case that the highest degree term under that radical will have the most effect on the end behavior. But we have to be careful with those signs. So let's think about the square root of 4x squared minus 3x plus 9. As x approaches positive infinity, the 4x squared term has the greatest effect, but it's under the radical. So what do we do with that? It's going to approach, like an asymptote again, the graph of the square root of 4x squared. Now we're assuming that we're moving to the right, so eventually all the x's will be positive. When we take the square root of 4x squared, we get 2 absolute value of x, and because we're approaching positive infinity, the absolute value of x is x, so we get 2x. Now, what happens when x approaches negative infinity? Again, to take the square root of 4x squared, we get 2 absolute value of x. But when all the numbers eventually become negative, to force it to be a positive value, we have to multiply it by a negative. And negative times a negative forces this to, in fact, be positive. So this is going to give us something different on the two ends of the graph. In this particular graph, you can see in black the graph of the square root of 4x squared minus 3x plus 9. On the left end behavior, you see the graph of the line y equal negative 2x, and on the right, the graph of the line y equal 2x. It has end behavior of 2 different functions because the square root had the variable underneath it. Let's put this expression in a fraction and see what effect it has when we go to infinity. Now, instead of simply being the square root, I'm going to have the square root divided by another expression involving x. Let's look at the limit as x goes to infinity. We know from what we did previously that the numerator will approach the square root of 4x squared. We know because it's going to positive infinity, and I'm just going to write that part for right now. that this is going to be the limit as x goes to infinity of 2 absolute value of x, which is just the limit as x goes to infinity of 2x. Now, what happens in the denominator? When we're looking at the denominator, what happens as we go to infinity? The graph of x minus 21 becomes closer and closer to just the graph of x, the highest degree term. So this approaches an x here, and x here, which means the graph must approach the horizontal line y equal 2. Now let's take a look at what happens on the left side as x goes to negative infinity. Let's think about what happens to these relationships we see up here. If I were to take these relationships as x goes to negative infinity, I could write, let me scroll up a little bit, the limit as x goes to infinity of the square root of 4x squared over x, which becomes, we're going to negative infinity, the limit as x goes to negative infinity of 2 absolute value of x over x. However, because the numbers are all now negative, to force that to be a positive number, I have to multiply it by a negative. And this means that it is approaching the graph of negative 2x divided by x, which gives me a horizontal asymptote on the left side of y equal negative 2. Let's now look at the graph and see if our suspicions were correct. You can see here on the right that the graph is coming down in red and approaching the horizontal asymptote y equal 2 from above. On the left side, it comes up from negative infinity. It has a vertical asymptote at whatever that is out there. And then it comes close, it approaches 0, and then it kind of goes back down again and approaches y equal negative 2. We have a different horizontal asymptote on the right than we have on the left. On the right, it's the blue line. On the left, it's the black line. Let's now take a look at example 8. Pause the video, work it out, then turn it back on to check your answer. So how'd you do? Did you get 3? Because you should have. In this problem, I only asked about the right end behavior as x approaches positive infinity. This is going to approach, not equal, but approach the graph of 3x divided by the square root of x squared, which is 3x over the absolute value of x. Because the values are eventually all positive, I can replace absolute value of x with x to get the right horizontal asymptote y equal 3. What do you think would happen if I looked at the limit as x approached negative infinity? The first parts would match down to the 3x divided by absolute value of x. But then I would have to replace the absolute value of x with a negative x in order to make that be a positive number, since all the x's would be negative. Then it would approach a horizontal asymptote on the left side of negative 3. Let's check out the graph and see if our suspicions are correct. You can see here the graph that we're looking at is in purple in the center. On the far right, it does indeed approach the horizontal asymptote y equal 3 relatively quickly. On the left, you'll notice that it does approach the horizontal asymptote of negative 3. Our suspicions were correct. Let's now look at example 9, which is the limit as x approaches negative infinity of numerator square root of 4x squared minus 1 divided by denominator x plus 2. We know that because we're approaching end behavior, we can ignore the lower degree terms and look at the ratio of the highest degree. square root of 4x squared divided by x. The square root of 4x squared gives me 2 absolute value of x, but because I'm approaching negative infinity, the x values are negative. To force them to be positive, I have to multiply by a negative, which gives negative 2x over x, meaning it approaches negative 2. Let's look at the graph if I can find the right one. This one. Here we go. And you can see here in the graph that it's not even defined in this region here. It must be the case that those values are giving us a 0 under the radical. Notice that as we approach negative infinity, it is approaching the value of negative 2. And as you may have suspected, on the right side, as x approaches infinity, it approaches positive 2 because we could replace the absolute value of x with just x. Let's now look at example 10. In example 10, we have the limit as x approaches infinity of 4x divided by the square root of x squared minus 1. Again, because it's end behavior, we can ignore the lower degree term negative 1, and we can look at the ratio of 4x to the square root of x squared. The square root of x squared is absolute value of x, but because we're approaching positive infinity, I replace the absolute value with x, which results in a horizontal asymptote of 4. What do you think would happen if instead I were approaching negative infinity? Everything would be the same to this step with the absolute value of x. But if I were approaching negative infinity, I would have to replace this with a negative x, which would lead to a horizontal asymptote of negative 4. And that, in fact, is example number 11. Let's take a look here at this example. When we're looking on the right side, because we replaced absolute value of x with x, we approached a positive 4. As we approach negative infinity, because we replace absolute value of x with negative x, we approach negative 4. Let's now go ahead and turn our attention to the last example that we have, which is example number 12. Example number 12 is rather more complicated than the previous examples. You may have been misled by the square root in the numerator and denominator and wanted to cancel them. And never allowed. If you have additional terms in either the numerator or denominator around that square root, hands off, it can't be canceled. In this case, we, again, because we have end behavior, want to look at the ratio of the highest degree terms. In the numerator, it's the only term we have, 2 square root of x. In the denominator, you can think of the square root of x as x to the 1/2 power. 1/2 is smaller than 1, so the highest degree term in the denominator is x. Then you want to reduce these two terms by thinking of them with their rational exponents, 1/2 and 1. This becomes 1 over x to the 1/2 or x to the negative 1/2, which becomes 2 over the square root of x. This is a constant over something going to infinity. Now the square root function looks like this right here. And as you know, it does grow to infinity, but slowly compared to the x squared or x cubed function. So we can expect that this graph will approach the x-axis, y equals 0, but slowly. Let's take a look at the graph and see if that is in fact what occurred. When we look at this graph, you'll notice that it is not defined at 0, and it is not defined for negative values because of the square roots. There's no red on the left side of the graph. And you'll notice I had to really stretch out the horizontal asymptote in order to get you to be able to see that it did approach 0. In fact, it should be stretched out even more, but then you lose the detail of what's happening here and the center of the graph near the origin. Our suspicions are correct. It does decrease to 0, but very, very slowly. Let's now turn our attention to infinite limits at vertical asymptotes. I want to make it clear that the only reason you can ignore the lower degree terms is because you're evaluating end behavior, where the x is approaching infinity or negative infinity. If x approaches one single finite real number, like 2 or 14 million, then you cannot ignore the lower degree terms. They could have a massive effect on the graph. When we're talking about vertical asymptotes, we are not talking about end behavior. Vertical asymptotes occur at single finite real values for x. This is where the number a is a 0 of the denominator in the reduced fraction. Let's take a look at a couple examples to make it clear when it's a whole and when it is going to be a vertical asymptote. In the example in the middle, you can see I have the factor x minus 3 in both the numerator and denominator raised to the same power. In that case, the x minus 3 factor cancels completely and is gone from the reduced fraction. When it disappears completely, this produces a hole in the graph at that x value, 3, with the y value being given by the reduced fraction when you substitute 3 for x. Now let's look at another example where we again have a factor in common, x minus 3, between the numerator and denominator. In the numerator, though, it's raised to the second power, and in the denominator, it's raised to the third power. There are more factors of x minus 3 in the denominator. When we reduce this, we will still have a factor of x minus 3 in the denominator. This is going to lead to a vertical asymptote at 3 and not a whole. Now let's take a look at example 13. I've gone ahead and written out some of this for you, and then we'll pause the video while you work out the remaining graphs on example 13. In this problem, we're not given the function, which is very problematic because if I'm evaluating what the limit is as x goes to infinity, I really can't tell. I don't know if it flattens out and approaches 1 or flattens out and approaches 4/5 or approaches 0, or maybe it just keeps going down forever and approaches negative infinity, but very, very slowly. I can't tell, so I put a question mark. I have the same problem on the left side of the graph. I can't tell what it's approaching, and it looks like I got my negative involved in my arrow there. I can't tell what's happening as I go to negative infinity because I don't have the equation of the function. The graph is not going to be enough to let me know for sure, definitively, what the limit is as x goes to negative infinity. However, on a vertical asymptote in the center of the graph, with center meaning just not in behavior, I can tell what the behavior of the function is. I have a vertical asymptote here at x equal 1. Notice the behavior on the right side and the left side of 1 is different. On the right, as I approach 1 from numbers above 1, the limit of the function goes to positive infinity. On the left, as I approach 1 from numbers below 1, indicated with the negative in the exponent position, the limit of the function approaches negative infinity. Go ahead and pause the video, work out the remaining graphs, put question marks on the ones where you feel like you cannot actually answer the question, and we'll compare our results. Let's see what you have. In this particular graph, I'm more confident about saying that the end behavior on both the right and the left is approaching 0 because of the way the function was written. the way that it gets super close to zero super fast. However, you could still make an argument that maybe it goes below and is actually approaching something different. When we look at the center of the graph, there are two vertical asymptotes at -2 and 2, and the behavior on each side of both of them is different. The limit as it approaches 2 from the right is infinity, but as it comes close to 2 from the left, the y value goes to -infinity. As we approach -2 from numbers to the right of -2, or take that back, that's -3. I missed my plus sign here. And I put it down there. Nope. I think I had it right the first time. Let's take a look. As I approach from the right side of -3, if I trace along the graph, yep, they go down forever. I had it right to start with. Then the limit approaches -infinity. As I approach -3 from numbers below -3, I've got this up here now and it shouldn't be there, then it does approach +infinity. Make sure you get the signs written correctly. Let's now take a look at the last two. The last two, if I look at the one on the left, again, I feel more confident in saying that the end behavior on both sides approaches 0. There are two vertical asymptotes at -1 and 2. As I approach 2 from the right side, it goes to infinity. But as I approach 2 from the left, it goes to -infinity. When I look at the approaches to the vertical asymptote at -1, whether I trace from the right or from the left, the y values decrease without bound, which means both one-sided limits as x approaches -1 become -infinity. We have one final example to do, and this is example 14. Let's now look at example 14. In example 14, we have x plus 1 divided by x squared plus 5x plus 4. We want to know what the behavior of the graph is as it gets close to -1. Namely, is there a vertical asymptote at -1 or not? Justify your answer without graphing. In this case, what we need to do is factor the function f and look at the graph that it approaches other than at any value that cancels. This is going to give me x plus 1, x plus 4. Now, these two functions are not equivalent because in the original function, I cannot use -1 for an x value. It causes 0 in the denominator. But it does cancel completely and disappear, which means that I must have a hole in the graph. And my hole is going to occur at that x value, which is -1. How do I find the y value? Well, to find the y value, replace the x with -1 in the reduced fraction, which gives me 1/3. Let's look at the function and see if that's what occurred. It's very hard to get Desmos to graph a hole. I had to plot the point -1, 1/3 in order to make it a hole. However, if you're not sure, you can click in the box for the particular function and then click directly on the point and it will tell you it is not defined there. That means it's a hole in the graph. Let's now look at the second example, x divided by x minus 2. I cannot cancel anything because I have two terms in the denominator, which means unless I can factor it out, I cannot cancel it. And there's no common factor to cancel out. This means the factor x minus 2 is in the denominator, so it's 0, x equal to is a 0 of the denominator. It doesn't cancel and reduce. This function stays the same, which means that I have a vertical asymptote in the graph at x equal 2. I did not give you the graphs for these because I didn't want you to cheat and use the graph to determine it. You won't have the graph on the exam. I want you to figure it out on your own. And it looks like I forgot to turn off the number here. And you can see right here that we do have a vertical asymptote in the graph at 2. We have one last example that we want to work in this section. And this is how to find the limit as you approach a vertical asymptote from the left and from the right. It's really an algebra problem, but we need to address it in calculus as well in talking about limits. Let's now take a look at this rational function, x plus 1 times the quantity x plus 5, all divided by x squared plus x minus 6. This is the ratio of two polynomials, so it's rational. In order to find whether or not there are any vertical asymptotes, we would take the denominator and factor it to see if any factors cancel and become wholes, or if they don't cancel and they stay vertical asymptotes. This would give me x plus 1 quantity times x plus 5, all divided by x plus 3 times the quantity x minus 2. None of these factors are common, and so nothing cancels and becomes a whole. However, we know we can't allow division by 0, so we'll have to exclude -3 and 2 from the domain. That makes these vertical asymptotes. I abbreviate vertical asymptotes with VA. Now we want to take a look at this function, and we want to decide what the function is doing on each side of these vertical asymptotes. For example, as it approaches -3, one of the vertical asymptotes from the left side, we know that it has to split and either go up forever or down forever. The limit will be either positive infinity or negative infinity. But how do we know which one? In order to determine that, we also need to consider other breaks on the x-axis formed by the graph. Namely, we need to look at x-intercepts. X-intercepts are solutions to the numerator polynomial, zeros of the numerator that don't cancel. That means that we have two x-intercepts, which are given by -1 and -5. When we think about finding the limit, then on one side of a vertical asymptote, we want to kind of draw the number line and fix on it the values that we know are on there so far. Here's my number line, and I'm going to draw a vertical asymptote at -3 and another over here at 2. However, we also know that -1 is on the graph. Let's make that in a different color so it will stand out. And also -50. When we're trying to decide what happens to the function just to the left and to the right of -3, we have to be careful to take a test point that's between the closest x-intercept and the vertical asymptote. Keep in mind that x-intercepts are places where the graph can cross over the x-axis from above to below or below to above. In doing so, it will change the sign of the y value. We need to test the y value close to the vertical asymptote to predict whether it goes to positive infinity or negative infinity. If you choose a test point on the other side of -5, you may get the wrong solution. In this case, we want to choose a value that's between -5 and -3 to come towards -3 from the left side. I'm going to choose -4. When I choose -4, what I'm going to do is I'm actually going to, well, I guess I should have left that. I'm going to substitute -4 into the function in place of the variable. I know that there's no x-intercept between -4 and the vertical asymptote. Thus, whatever sign it has at -4 must be the sign that it keeps. So if it's positive, it must be going up forever. And if it's negative, it must be going down forever. Most of the time, you don't need the actual value. What you need is the sign. In this case, I have a negative times a positive over a negative times a negative. That gives me 3 negatives, which tells me that it's negative. That means that at this value, it must be coming down and looking something like this. Now I want to see about the limit as I approach -3 from the right side. Again, I need to take a test point, but it has to be close to the vertical asymptote on the right and not beyond any x-intercept where the graph could have changed sides. I have an x-intercept at -1, so I need to choose something between -3 and -1. So I choose -2. Now I test -2 in the function to find out whether the y value there is positive or negative. In this case, I get a negative times a positive over a positive times a negative. I have 2 negatives, which makes the whole thing positive. And that means that this will be going to positive infinity. I guess I should finish this one here and write the solution. That means that it's got to be doing something like this as it approaches that value. Now that we've discussed how to find it when you are getting close to an asymptote, pause the video and work out what the limit is on either side of 2. Then turn the video back on and we'll compare our results. Let's now see what we got. Since I'm approaching 2 from the left side, I need to choose something that is between the closest x-intercept at -1 and 2. I could have chosen 0, which probably would have been a better choice, but I chose 1 instead. That gives me a positive times a positive over a positive times a negative, which makes the whole thing go to -infinity. So it must be coming down and crossing and going below. This also implies that the y-intercept must be negative because it never crosses the x-axis again. On the right side of 2, I can choose any value I like because there's no x-intercept to the right of 2. I chose 3 as the simplest number, which gave me all positive factors, so I know it goes to positive infinity. Lastly, if we were to multiply it out, we would have the ratio of leading coefficients x² divided by x², which tells us that it has a horizontal asymptote of y = 1 as it goes to infinity. This is the end of this section on infinite limits and limits at infinity. In the next video, we'll be studying continuity. Continuity is one of the most important concepts in calculus. The reason being that many of the major theorems in calculus require continuity as a condition of using the theorem. If it's not continuous, you can't use the theorem. Now, continuity means that you can draw the graph without picking up your pencil, which means that a hole or a displaced point or a jump or a vertical asymptote, we have a break in continuity. Join me for that video.